Hi there. In this video, we're going to have a look at linear equations, what they look like, and how we can solve some problems that are linear equations. The first thing to point out, I guess, is that linear equations have order 1. And what that means is that if we have a look at the variable in the equation, it's raised to the power of 1. So this, for example, is a linear equation. This one isn't because we've got 3t squared. Okay, so that means that it's not a linear equation. This one, the x here has order of 1 and the x here has order of 1, but if I expanded it, you could see that the x times the x would give me an x squared. So that is not a linear equation. This one similarly kind of looks like it might be a linear equation, but because the x is on a denominator here, if you remember your basic index laws, that would actually make it 3x to the power of -1 here. So that is not linear either. So you've got to be very careful that it has to fit a very specific pattern to make it equal to a linear equation. So that's the first property. The other thing to point out is that a linear equation has only one solution, sometimes none, depending on how it's set up, but generally it has one solution only. If you have two variables in the linear equation, then we have this thing called constant proportionality to each other, which means that as one variable changes, the other one changes at a constant rate. And a classic example of that is like a linear function like this, y equals 2x plus 1. You might remember that 1 is the y-intercept and that 2 is the gradient, and that if I drew this, just really roughly 1, it would go up like so, so that as x changes, like if x is equal to 1, then there's a change of, so x changes here, there's a change of 2 units in the y direction. And if I go another 1 unit here, so up to 2, there is a change of 2 units again for the y. So that change in y is constant. It's the same value, and that's what constant proportionality means. Okay, so we're going to go through a couple of examples now just to give you a sense of the kinds of problems. Now, we will look at linear functions in more depth as we go along. This is just to get you started, really. So here's a problem from the textbook. The sum of two numbers is 42. So we've got sum. If we don't know what sum is, we're in trouble. So that always with problem solving, the first thing we have to ask ourselves is, do we understand the question? So that's a language warning. The sum of two numbers is 42. One number is twice the other. So it would not hurt, particularly in exams, if you start getting a highlighter out and highlighting important facts to try and get that out. The next thing we tend to do with word problems like this is in our solution, we tend to set up the variables. Now you can do it formally or informally. I like to be a little bit formal, so I say something like, let n be one number. Then, now it says one number is twice the other, so that means the other number must be 2n, if that kind of makes sense. Be the other number. So n is the smaller number, 2n is the larger of the two, and it says the sum of these two numbers is 42, and so I go, therefore, n plus 2n is equal to 42. So I've used the other fact in the problem in order to write it as an algebraic expression, which I then simplify, and then I solve. I divide both sides by 3 to get n is equal to 42 divided by 3 is 33, 36, 39, 42. Okay, so it's 14. Answer the question is the last thing. It says find the two numbers. If you leave it as n equals 14, you haven't. I really do prefer, excuse me for the squishy room here, but I really do prefer there to be a little bit of just a little bit of a sentence to finish off. So something like, so therefore, I'm squishing it in, sorry. One number is 14, the other is 28. Something like that, just to bring it all together. Always ask yourself, did you answer the question? Let's go through this next one. Example 2 says find 4 consecutive odd numbers with a sum of 80. Now, this idea of an odd number and how do I express that algebraically is pretty common, which is why I'm just going to spend a moment going through that. The other key word, I guess, is consecutive. So if you don't know what that means, then it means one after the other, like 2, 3, 4, 5 are consecutive numbers, 2, 4, 6, 8 are consecutive even numbers. And of course, sum of 80 is the other critical bit as well. So I'm just going to highlight that as well. I probably should have highlighted the fact that it says 8 odd as well. So here's a little trick, I suppose, that that's worth looking at. So let's let n be a number, any old number. If you like, a whole number, an integer. So if I let n be any number, then 2n will be any even number. You think about it. You take any old number you want, a whole number, and then double it. You'll always get an even number. This will generate every single even number. So if I let n equal 0, then 2n is 0. If I let n equal 1, then 2n equals 2. If I let n equal 2, then 2n equals 4. So I get 0, 2, 4, etc. So this would generate all even numbers, but we don't want the even numbers, of course. We want all the odd numbers. Well, what's the difference between an even and an odd number? Well, an odd number is one more than an even number. So 2n plus 1 would give us 1, 3, 5, 7, and so on, depending on the value of n. So basically, this means 2n plus 1 is an odd number. To get 4 consecutive odd numbers, then we're just going to have to go up 2 at a time, right? So if 2n plus 1 is the first odd number, then the next odd number is going to be 2 numbers across. So it's going to be 2n plus 3. The fourth one is going to be 2n plus 5. And the fourth one is going to be 2n plus 7. I might have said fourth before. So first, second, third, fourth there. Okay. So that's how we generate 4 consecutive odd numbers. It's a trick and it's a common one to use 2n plus 1 to describe an odd number and 2n to describe any even number. So we're told that these consecutive odd numbers have a sum of 80. We need to know sum means add. So I add them together. I might just do this bit in my head and just get it all down really quickly. So 2n plus 2n plus 2n plus 2n is 8n. And then let's add up the numbers. 1 and 3 is 4, and 5 is 8. 1 and 3 is 4, 4 and 5 is 9, sorry, and 9 and 7 is 16. So we've got 18 plus 16 is equal to 80. We've got 18 is equal to, so we'll take 16 away from that. So that'll leave me with 74, 64, and then divide both sides by 8 to get n is equal to 8. That's what n is equal to, but what we're interested in is what the 4 consecutive odd numbers are. So I'm going to conclude, therefore, the numbers are, always answer the question. So n is equal to 8. So if I look at the first odd number, it's going to be 2n plus 1. So I go 2 times 8 is 16 plus 1 is 17, and then I can work out the rest just by using logic. 17, 19, 21, 23. If you really want to, you can substitute in to make sure that 2n plus 7 would give us the right answer, but that's basically it. Okay. Example 5 is one of those proportionality things, and we're looking at a problem here from towards the end of the textbook, page 546, example 4. And you're asked to consider a speed problem. So a car travels from Copenhagen to Shalagam, which is a distance of 150 kilometers. Okay, so I might just highlight that. So 150 kilometers in 2 hours. Assuming the car travels at a constant speed, draw a distance time graph and calculate the speed. Now, when you have a look at the example in the textbook, it seems to assume that we would want to map minutes versus kilometers. I don't understand why. Maybe there's a good reason for it, but I'd prefer to map, get rid of that. I'd prefer to map kilometers versus hours, to be honest, because after all, is that not what we normally calculate speed in? So we know, so just drawing the graph, we can call this O for the origin, where they start off with, and then we can say, okay, let's make this 1 and let's make this 2. I'm trying to keep my proportions right on my diagram here. And I know that after 2 hours, they've traveled 150 kilometers an hour. So I'm just going to, there's no real rhyme or reason except that I'm just going to call that 150. And then I'm going to draw a line here. Now my line tool's a bit dodgy, so just see how I go. There we go. I missed it by a little bit, but it's pretty close. So we can say that's the end point. And if we want to use X marks the spot for the end point, we could do that like so. Okay, so we've got X marks the spot at the end there. Now that's a distance time graph because X represents distance and Y represents time. I could have instead, I'll just do it in a different color. I could have instead maybe called it a D for distance graph and a T for time. That would be entirely appropriate. We don't have to stick to X's and Y's. And do note that, as usual, this axis represents the dependent variable, and this represents the independent variable, whether you call it XD or T or Y. I'll just start that one again. Sorry, that is of course round the wrong way. This is T and this is D, and distance is dependent on time. Okay, so either way would be absolutely fine. I'm just going to go down to slide 11 here to finish off because we're asked to calculate the speed. And we know that the speed is distance over time. So we can then say speed is equal to distance, 150 kilometers, over time, which is 2 hours, and 150 divided by 2 is 75. So it's 75 kilometers per hour is how we would write that. Or if you like, 75 kilometers per hour with a -1 there, either way. And we can sort of get that on the graph as well. This is this constant proportionality thing that if I go up from 1 hour, assuming my graph is pretty accurate, which it probably isn't terribly, then we see that we are halfway, we should be halfway up here, which would be the 75. I'll just write that in green so we know it's not an official number there. And that's the constant proportionality, that as the speed, as each hour passes, 75 kilometers is also traveled. Okay, I'll leave it there, and yeah, I'll see you for the next video.